Hi, my name's Nikhil Shinde. I'm a PhD student at UC San Diego, and today I'm presenting our work, JIGGLE. Consider the problem presented by these two deformable tissues. Now, just by looking at them, can you tell me where they're attached to the environment? No, right? To do this, you need to actively interact with the environments. And the natural next question is, well, what actions should you take next to uncover more? These are the questions surgeons think about all the time. They constantly manipulate tissues in the environment to understand the structure and attachments. This is as a large part of operations are spent either removing or creating these attachments. Inspired by this, we present JIGGLE. Our method uses the discrepancy between simulated and observed interactions to compute a probabilistic update on boundary attachments and inform safe future actions. Our method is divided into two parts. We're going to start by talking about estimation. Our method leverages a fully differentiable PBD simulator. We model our boundary attachments as springs of varying strengths that attach the tissue to virtual particles that are fixed in the environment. We use an extended Kalman filter to probabilistically track these boundary attachment parameters. The key component of computing these updates involves computing the Jacobian matrix, J, which we efficiently compute by leveraging our differentiable PBD simulation. We demonstrate our estimation method on real-world experiments. We sutured chicken skin onto pieces of chicken thigh to create attachments. Notice the uncertainty decreases in the deformed regions shown in blue, while the estimated attachment points shown in purple began to closely match the sutured region. Now we move on to active sensing. Our active sensing algorithm aims to maximize information gain by deforming uncertain areas of the tissue while respecting safety-critical constraints in surgery. To select the next action, we iteratively refine large action samples using gradient updates before selecting the best sample and taking a step in its direction. Here we show some results in simulation on active sensing. The video shows regions of increased confidence in blue, and the graphs show entropy reduction and boundary energy over time. Notice how our method takes actions to intelligently decrease the entropy while keeping the boundary energy below a certain level. The estimated shape uncovered by our active sensing strategy matches the partial ground truth. Our approach also supports topological changes in the boundary conditions such as cutting. We incorporate priors on topological changes into the Kalman filter's motion model. Here we show an example where we use our method to iteratively estimate and cut attached regions of the tissue. Despite its success, our method is still limited to thin shell tissues due to perception challenges like volumetric occlusion and unobservable internal 3D structures, leaving room for future work. Thank you for listening to our talk.